We don't see the global scale plate tectonics that we're familiar with on Earth anywhere else in the solar system. Earth has a particular set of features that enable mantle convection and plate overturn across the whole planet. But that's not to say that we don't see tectonic activity of other kinds. Today, we're going to examine two unique examples of tectonic activity, their associated structures, and the processes that drive them. First, we'll examine the satellite Enceladus. Covered in ice, it's the sixth largest moon of Saturn. The consequences of tectonic stresses depend on the properties of the material being stressed, i.e. its rheology. The rheology of any given material is dependent on its temperature relative to its melting point. On Earth, ice is rarely at a temperature less than about 80% of its melting point, but on the moons of the outer planets, ice is at a temperature of around 40% of its melting point, similar to that of rocks at the surface of the Earth. So at depressed temperatures, ice behaves in a way analogous to solid rock. A broad range of crater densities indicates that Enceladus has had a long and at least intermittently active tectonic history. The North Polar region is heavily cratered and apparently undeformed, but the South Polar region is uncratered and marked by intense tectonic deformation. The lack of craters indicates that this surface is only a few million years old. The South Polar region of Enceladus exhibits many similarities on a large scale with rift basins found on Earth. The characteristic structural components of rift basins, including a depressed floor, sometimes relatively flat and faulted, border faulting, uplifted flanks, and transform zones, are all matching features. The most prominent features of the region are a set of subparallel troughs up to half a kilometre deep, 2 kilometres wide, and around 130 kilometres long, bound by ridges on both sides. Known as the tiger stripes, they seem to have formed originally as tension cracks, since they're oriented perpendicular to the maximum stresses currently affecting the crust. There's some evidence of right lateral shear along these fractures, but no offset has been observed directly. Separated from the rest of the moon by large scarps, the southern polar region is an area of high heat flux and extensional tectonics. Jets of water vapour and ice are ejected into space from the tiger stripe rifts. The margins of the region are scalloped and marked by wedge-shaped scarps that are probably fault and thrust belts. The pattern of extensional rifts at the centre of the region, bounded by compressional features, and the high heat flux suggests that a convecting mantle plume underlies the South Pole and drives the tectonic activity. It's still uncertain whether the convection is occurring in plastically deforming ice extending all the way to the silicate core, or in liquid water as part of a subsurface ocean. Warm, buoyant material in the centre of the region rises and drives the extension, while the cold boundaries sink and are eventually recycled. In contrast to the South Pole, the oldest region on Enceladus is a band of ancient, heavily cratered terrain that forms a belt running from the Saturn-facing side of the Moon over the North Pole and down the opposite side of the Moon to the margin of the South Polar region. This band defines two hemispheres, one in the direction of orbital motion and the other in the trailing direction. These two regions are intermediate in age between the currently active South Pole and the ancient cratered belt, tectonically deformed in a similar way to the South Polar region and showing evidence of a regionally elevated heat flux in the past. These regions seem to record a history of tectonic resurfacing similar to the activity seen today at the South Pole. Enceladus's patchwork appearance makes it obvious that tectonism is occurring regionally, not globally. Localized areas of thermal energy can accumulate over hundreds of millions of years, all to be released over a relatively short period of only a few million years, with intense regional heat loss, tectonic overturn, and volcanism. These two modes are known as static lid and mobile lid. Unlike the constantly mobile plates on Earth, most of Enceladus's crust remains immobile and effectively seals in the heat generated by tidal interactions with Saturn. Over time, the upwelling mantle plume, driven by heat in the interior of the Moon, thins and weakens the ice shell until it fractures. The crust becomes mechanically coupled to the motion of the plume, deforming the surface of Enceladus. The heat loss associated with this phase of the cycle depletes the energy reservoir built up, and eventually, the surface refreezes to a thickness where the Moon returns to its energy storing phase. At the present time, we are witnessing the heat loss and resurfacing mode. Enceladus is unique amongst the bodies of our solar system in that it is a currently geologically active and heavily deformed satellite that records a history stretching from the present day to billions of years in the past. Our understanding of the processes in play in Enceladus is limited by the paucity of data. Everything we know about the moons come from the flybys of the Voyager and Cassini missions. We still lack a full understanding of the global geological story of Enceladus. We've seen enough to know that its tectonic history is vastly different to that of the Earth.
Io. Like Enceladus, Jupiter's third largest moon is a tectonically active body that has given an insight to an alien example of structural geology. With over 400 active volcanoes, Io is the most volcanically active body in our solar system. Similar to the size of our moon, it is also the densest natural satellite with an iron core and silicate mantle. I's topography is a result of extreme volcanism caused by heating from internal tidal stresses due to Jupiter's gravitational pull coupled with the orbital interactions with the other moons. Io's crust is surprisingly young, only 1 million years old. Constant volcanic resurfacing covers any past impact craters during its rapid recycling. The surface is mainly comprised of lava flows, calderas, layered lava plains, and mountain ranges and plateaus. Volcanic plumes expel sulfur and sulfur dioxide, which give the moon its unique color. The hundreds of mountains across Io's surface are incredibly tall, the highest reaching 17 kilometers, exceeding Mount Everest. But these mountains cannot attribute their height to volcanism. There is no positive correlation between the mountains and distribution of volcanoes, to the extent that there appears to be more mountains where there are fewer volcanoes. The process of mountain building on Io is related to the moon's volcanism, but not directly. Regions of active volcanism expel large amounts of mantle material onto the surface, bearing older crust and pushing it downwards. Layers that were once on the surface no longer fit the decreasing surface area as they descend into the interior of the moon. The combination of downward compression and thermal expansion adds to the overall compressive stress on the base of the lithosphere. The shrinking crust eventually fails under this stress, producing thrust faults. The uplift from these faults form region-scale crustal tilt zones. These tectonically formed mountains are similar to the basin and range provinces found in the western United States. Some of the moon's mountains resemble mesas or plateaus, but most are steep-sided tilted blocks of crust undergoing tectonic collapse. Mountain scarps are directly produced by thrust faulting, or in conjunction with thermal uplift from reheating of the crust. Geologists look at the structural processes that causes thrust faulting on Earth to understand the mountain building on Io. Thrust faults are formed when the crust is subjected to compressive stresses until it fails. Lower stratigraphy is pushed on top of higher, which can often be identified by older rocks appearing on top of younger in the stratigraphic record. The compressive forces on the Earth that form thrust faults are the result of the planet's unique plate tectonics, but Io does not have separated into plates on a convecting mantle. Io does not have a lateral tectonics like Earth. There are no subduction zones or spreading ridges. There are no discrete plate boundaries, and the mountains we observe are not distributed in linear patterns of orogenic belts, as we see on Earth. The thrust faults on Io are driven by regional compressive shortening of the crust due to horizontal shortening as the global concentric layers of the older crust compact and shrink. Since we observe a relatively uniform distribution of volcanoes, we can infer that these compressive stresses will also be uniform within the lithosphere. Uniform stress in a thick lithosphere is relieved locally through thrust faulting occurring at local failure points like volcanic intrusions, pre-existing faults, or areas of high thermal stress. Over time, mountain formation will occur globally in apparently random distributed locations. Let's walk through the formation of a typical Ionian mountain. First, volcanic material is expelled from the interior onto the surface. The buildup of volcanic material thickens and weighs down the crust. Compressive stresses build up as the crust is forced to fit more material into a shrinking space. The base of the crust is then experienced thrust faulting. Some of these faults may reach the surface. Softening and melting at the base of the crust produces more uplift and further tilting. Ultimately, the thermal erosion of the blocks leads to the collapse of the mountains. Volcanism continues and the cycle begins again. Io is a fascinating look at the plate tectonics, both familiar and strange. The formation of the moon's large, isolated mountain peaks is closely linked to the high heat flow and rapid rate of volcanic resurfacing. The chaotic and globally rapid tectonic overturn of the surface may give us an idea of what Earth looked like in its early history.